So good morning Year 10 and welcome to this, the third lesson in C3 Quantitative Chemistry. So last week we introduced the idea of the conservation of mass and the fact that reactants and products had to have the same mass. And then we went on to look at the really important fundamental concept, relative formula mass. And that is something that you will need for the rest of this topic. Today we're going to look at a practical, the oxidation of magnesium, and we're going to do a small amount of maths to predict the mass of the product. But before that, let's have a look at the homework. As I record this, I've got about 45 responses on this relative formula mass homework, so that is just under half of you. You can see though that out of 18 marks, the vast majority of you are scoring very, very highly. The median is 17 out of 18, which is great. There are, however, a few people who are scoring very poorly on these relative formula mass. And to those people, I say you really must work out what your mistake is. Let's look at some of the common errors. The first error that was quite common, 10% of you, was a rounding error. The correct answer was 89%, rounded correctly, but many of you saw 88.7 and just said 88%. Can I remind you that in an actual exam, that's not okay. You need to round your answers correctly. The second mistake, you can see quite a lot of people here giving a percentage that is half of what the actual percentage is. And this is again people not realising that in calcium nitrate there are 3 times 2 which equals 6 oxygens. The most common error so far though was the formula mass of substance Y. The correct answer, 30, was given by 50% of people, but double the formula mass, 60, was given by a very healthy 20%. And this is of course because people forgot that the reaction made 2 lots of Y, so the mass that you worked out that was missing had to be divided by 2. Nevertheless, a very good job from most of you, showing that the vast majority of you have understood and can apply the concept of relative formula mass. The practical we're going to do today is the oxidation of magnesium. So first, write a balanced chemical equation, including state symbols, for the reaction of magnesium with oxygen gas. Then 2, work out the relative formula mass of each species in the chemical equation and show that your equation obeys the law of conservation of mass. I strongly advise you to pause the video and have a go at these questions before continuing. Okay, the balanced chemical equation for the reaction of magnesium and oxygen. Magnesium, which is a solid, reacts with oxygen gas, which is, don't forget, O2, it's diatomic. Oxygen as an element always goes round in pairs, and you know why from C2. It's so it can end up with a full outer shell of electrons and can be stable. So for those of you who have already forgotten C2, it forms a double bond to fill its outer shell. And the product, magnesium oxide, again, I hope that you work that out without too much trouble. Magnesium is in group 2, so it forms the 2+ ion. Oxygen is in group 6, so it forms the 2- ion. So it's a 1-to-1 ratio MgO. And again, you could do a dot cross to show the magnesium with an empty outer shell and a 2+ charge. Oxygen with its own 6 electrons plus 2 from magnesium and a 2- charge, and you should be able to do that by now. So anybody who is unable to work out the formula of magnesium oxide, again, you need to go back and recap some of your previous topics, particularly C2. Because we've got 2 oxygens on the left, we need 2 oxygens on the right, hence 2 MgO. If we have 2 MgO, then we need 2 magnesiums on the left. As for the relative formula mass of each species, well, there's 2 lots of magnesium, each one is 24, so 48 grams per mole. Oxygen, O2, 2 times 16, 32 grams per mole. And they add up to mean that the reactants have a relative formula mass, 80 grams per mole. Looking at the products, well, magnesium oxide is 16 plus 24, which equals 40, and there's 2 of them, so that sums up to 80 grams per mole as well. Happily, the reactants of the products have the same mass. Great. But now we start to get a bit more interesting. If we started with 24 grams of magnesium and we heated it strongly so it all reacted, what mass of magnesium oxide would we make? What would be the mass of the product? Well, let's go back to the equation and the formula masses of the magnesium that we start with here. So magnesium that we start with, formula mass of 48 grams per mole. The magnesium oxide that we end up with, 80 grams per mole. So 48 grams of magnesium becomes 80 grams of magnesium oxide. So what would 24 grams of magnesium become? Well, hopefully you have realised that if 48 grams of magnesium becomes 80 grams of magnesium oxide, 24 grams of magnesium, which is half that, so 24 is half 48, would become 40 grams of magnesium oxide, which is half of the 80 grams there. Your turn. If we start with 2.4 grams of magnesium, what mass of magnesium oxide would we make? Have a think. Check you can work this out. Well, if 48 grams of magnesium becomes 80 grams of magnesium oxide and 24 grams became 40 grams, what would we expect 2.4 grams to be? 2.4 grams of magnesium would become 2.4 over 48 times by 80. So the 2.4 over 48, that's the fraction of the 48 grams per mole that we have to start with, because we know 48 grams becomes 80. So if that's the fraction that we start with, then we multiply that fraction by the formula mass that we would have got if we'd started off with 48, and we get 4.0 grams. 4 grams of magnesium oxide. Now some of you here might be screaming for a formula, and I'm not going to give you one because I want you guys to understand what we're doing here with the maths. We're saying that if 48 grams becomes 80 grams of magnesium oxide, we just need to be able to work out the fraction of that we start with, which will be the same fraction of that we end with. Finally, let's have some slightly less nice numbers. If we start with 1 gram of magnesium, what mass of magnesium oxide would we make? Again, 48 grams of magnesium becomes 80 grams of magnesium oxide. So what does 1 gram become? What's the same ratio as 48 to 80? Hopefully, by now you've got the idea. The fraction of that we start with is 1 over 48. We times that fraction by the 80, and we get that 1 gram of magnesium would become 1.67 grams of magnesium oxide. This is just a ratio calculation. You've done it in maths before. 2 to 10 is the same as 4 to 20. is the same as 1 to 5. It's just using ratios to work out the amount of product that you would make. Do make sure you understand this and how you do these calculations, because you're going to need them for the next couple of lessons. Now let's have a look at the practical equipment that you're going to see in the video. We've got the magnesium, which we put in a coil into a dish called a crucible. And the crucible is a dish and lid that is used for heating very, very strongly. The crucible is sitting in a holder called a pipe clay triangle, or a clay pipe triangle, depending on who you are. And that is supported by a tripod. The magnesium is heated extremely strongly over a roaring Bunsen flame until there's no more change in mass. And then we can investigate what is the mass of the product that is formed. So what we do is we weigh the magnesium at the start of the experiment. We then weigh the magnesium oxide at the end of the experiment, and we're going to see whether the gain in mass matches your predictions. So what is your prediction? Well, here's your prediction. We're going to start with 0.12 grams of magnesium ribbon. Using the calculations you've just done, what mass of magnesium oxide should 0.12 grams of magnesium make? Don't move on until you've sorted this and you've got an answer. Okay, let's watch the video. So hello again, Year 10, and today we're going to do an experiment where we're going to calculate the change in mass during a chemical reaction, and we're going to see whether that agrees with our calculations using our relative formula masses and our conservation of mass ideas. So the experiment we're going to do involves the oxidation of magnesium, very similar to the experiment you saw last time, burning the iron wool. And the first thing we need to know is what mass of magnesium we are starting off with. So on the balance here, 0.12 grams of magnesium. Now, just to make sure that this heats efficiently and effectively, the first thing Miss Richardson is going to do is she's going to coil it into a little spring shape. What would you call it? A spiral? Yeah, spiral rather than the helix. And then she's going to put that spiral onto the bottom of what's called a crucible. Now, it's quite likely you guys haven't used a crucible before. These are designed to be heated very, very strongly. Now, before we start heating, we need to know the mass of the crucible as well, with the lid. So let us weigh the crucible plus lid, 31.52 grams, and this will let us know easily any changes in mass. So 31.52, note that down now. Right, now Miss Richardson is going to turn this up to a roaring blue flame and start heating the crucible. And we do need this to get extremely hot. So we're using the crucible supported within a clay pipe triangle there. So that you can see there it's a clay pipe triangle. And also notice the way that it has been positioned on the tripod. That is the Star of David formation, as it's called, with the metal prongs from the clay pipe triangle sticking over the middle of the tripod. Don't be tempted to balance this the other way round with those metal prongs. Could you just point to a metal prong? Yes, with those pointing to the corners of the triangle, or you will end up with everything falling through. Now, the idea here is that we are actually going to heat this crucible until the bottom of it is glowing red hot. So just going to heat it a bit more just to ensure that that really is glowing beautifully cherry red. Now occasionally Miss Richardson is going to use tongs to lift the lid off. So let's have a quick look inside. It's not glowing red yet, nowhere near hot enough. Now one of the big sources of error in this experiment is the fact that we can lose product if we are over eager in lifting off the lid of the crucible, and we don't want to lose any product or we won't be able to accurately weigh the crucible and the lid and the contents at the end of the experiment. So what we need to ensure is that we only lift the lid occasionally and we don't lift it off so fast or with such force that we actually cause any of the product inside to go flying out of the crucible.
It's just starting to glow on the bottom.
Just starting to glow on the bottom now? Oh yeah, we can see a lovely cherry red colour, and I'm going to look in from the top now. There we go. Oh, right now, there, did you see the magnesium glowing beautifully yellow there? Beautifully white hot. And so we're going to put the lid on, we're going to let it heat a bit longer, and Miss Richardson is going to sporadically, maybe once every 30 seconds or so, lift off the lid and see whether the magnesium reignites.
That's a yes?
Yep, if it keeps igniting, then we know that the reaction hasn't finished. Now, she's not leaving the lid off, because as I said before, we don't want to lose any of that product. There you go,
Yep.
It's still reigniting every time that lid is taken off, so the reaction has not yet gone to completion.
Yep.
Now there, you saw, as that lid was lifted off there definitely was some smoke came out of that. And just bear that in mind as a source of error in this experiment. We are going to lose some product as the hot fumes cause some of the product to drift up out of the crucible.
That's almost done, I'd say.
Oh, I don't know. Oh, look at that. That's still glowing beautifully. And yeah, look at the cherry red colour at the bottom of the crucible. So that must be about 600, 700 degrees, that pot. So obviously one of the things to be aware of is just how hot the materials in this experiment are getting, and there are all those safety implications, hence the lab specs worn by Miss Richardson.
Yep,
Okay,
still glowing.
Still glowing, still igniting there. This is showing beautiful patience from Miss Richardson, because often students at year 10, bored with the experiment, will just take the lid off, let the reaction go in one blinding flash, and then weigh, obviously losing quite a lot of their product in the process.
It's what 8-hour university practicals do to
Oh, there you go, still glowing beautifully.
Almost there though.
Almost there. And again, this can be beautifully cut down.
Yeah, do a speed up animation. I would go as far as saying that's almost.
Yeah.
Almost done. There's no
Okay. So we're going to turn that to a safety flame and remove the heat.
I'm just going to turn the Bunsen off.
And now we're going to let it cool down. Okay, so we've let the crucible cool down, and Mr. Reeves would really like to highlight to you Year 10 students that Miss Richardson has put it sensibly on the heat-proof mat to cool down. She hasn't stuck it on the desk, as this one here, because, as I said, it was 600 or 700 degrees. Now we're going to weigh it. A reminder, before the practical, the contents, including the lid, were 31.52 grams. So let's see whether it has gained or lost mass. So 31.52 initially. 31.56 grams, okay? So that has gained mass. Now what Miss Richardson is going to do is she is going to stick it back on the Bunsen burner and she's going to heat it again to see if a bit of further heating to cherry red will cause any increase in mass. Okay, so after heating it back up to cherry red again, opening the lid a couple more times, we're now, and letting it cool down of course, we're now ready to see whether it has gained mass in this second weighing. Well, should we use these scales? Because these were the ones we used before. 31.60 grams. So the contents have gained in mass by 0.08 grams. Now, obviously, if we had the time, Miss Richardson would heat it up again and then try this again. That is what's called heating to constant mass, but that gives you an idea of the practical. Once again, thank you, Miss Richardson, and thank you, Mr. Reeves.
It's my pleasure.
Right, hopefully you paid attention. If you didn't make notes, then you may need to go back for the rest of this lesson and re-watch that video more carefully. But let's run through the results. We weighed the magnesium at 0.12 grams. We then weighed the crucible plus the lid plus the magnesium, which weighed 31.52 grams. So, what is the mass of the crucible and lid by itself? Well, hopefully you've realised that it's 31.52 grams minus 0.12 grams, which equals 31.40 grams. Now we could have weighed that directly, but we forgot to do that at the start. Nevertheless, we could work it out. So the crucible and lid weighed 31.4 grams. At the end of the experiment, the crucible plus the lid plus the product weighed 31.6 grams. So what was the mass of the product? Well, if the crucible plus lid plus product, crucible plus lid plus product weighed 31.6 grams, then taking off the mass of the crucible and lid means that the product weighed 0.20 grams. And notice I'm writing 0.20, not 0.2 grams. It's important now, as GCSE students, that you start using the right degree of precision in your answers. We've weighed it to 2 decimal places. We should give our answers to 2 decimal places. So, did that agree with your calculations? Only you will know that. Hopefully you did do some calculations and a prediction at the start. For the rest of this lesson, you're going to do the write-up. Now, the next 2 slides show the sheet that you would have been given had you been in the lesson doing this practical. So let's have a quick look. Practical. The mass change when reactant is a gas. Aim to investigate the change in mass when the reactant is a gas. Hypothesis. Well, that's very straightforward. What did you think was going to happen? Reaction equations and the theory. Well, we covered those at the start of this lesson. So, what is the equation for the reaction of magnesium and oxygen? And why do you think that that equation explains your hypothesis? So, if you said you hypothesize that the reaction was going to gain mass, why? Why does the reaction equation tell you that? This is important. Predicted mass of product. What did you think you were going to make based on your calculations? Here we've got hazard, risk and precaution. You can give 1, 2 or 3. What did you think was the main hazard? So remember, the hazard is the thing that's going to do you harm. So a hazard might be cut glass. The risk, do you think that this is likely or very unlikely? I would say, given we didn't use anything with glass, it is unlikely. What's the precaution? How do you reduce the risk even further? Keep glassware away from the edge of bench. Now, this is not an appropriate hazard, risk and precaution for this practical. You need to think, what is the most serious hazard in this practical? How likely is it that someone's going to get hurt? And what is the best precaution to mitigate that hazard? So this is not the right one, but you need to think what is. On the second half of the write-up, a quick method. What did you do? And results. What was the mass of the crucible? Well, as we said, the mass of the crucible was 31.40 grams, and that included the lid. The crucible and the magnesium was 31.52 grams, and the magnesium was 0.12 grams. The mass of the crucible at the end was the same, 31.4 grams. The crucible and the product was 31.6 grams. So the magnesium oxide 0.2 grams. So the change in mass was plus 0.08 grams. Discussion. 3 questions. Single sentence answers should be fine. Was there an apparent increase or decrease in mass, and why? This is important. They often ask about this. How could you ensure that the reaction was complete? We did explain that in the video. If you can't remember, go back and re-watch it. How did we ensure the reaction was complete? And here, did the final mass of product agree with your predictions for the balanced chemical equation? You need to answer that. Another really common question, why might the increase in mass be less than expected? A very common question. Why might this change in mass plus 0.08 grams have been less than expected? I'm not telling you whether it was, but why might it have been? That's what you have to do for today. Make sure that you understand everything you did, because you're going to do a very similar experiment in your next lesson, but I'm going to give you far less help with the calculations and how to write it up. So if you do struggle, please email me to ask for help. Good luck.